get started. This is where we were last time. We're going to go back to the simulation in a second so you can see what everything I write on the chalkboard is actually doing. I think it's pretty cool on the chalkboard, but I think it's really cool as a visual. You can see all the flexibility sometimes you get with Bayes. Now, of course, that depends on how flexible your likelihood is and how flexible your prior is. So I kind of mean how your likelihood parameterization reflects what's going on in the data. And so I'm going to talk about that a little bit later, but I want you to recognize that the likelihood function comes from the sampling distribution. So I take the sampling distribution of joint X, and then I plug in joint all of X, all of my data. So I'm calling this joint X. My joint data. I plug it into the sampling function, and then I think about the parameters is something that I want to learn about. And so this same function has all the information about X given P, also has information about P given X. And that kind of makes sense. So there's a relationship there. I say that that makes sense. This was hotly contested for a long time. What's this likelihood stuff? And a lot of people that did write about it in the literature usually came back around and said, okay, that makes sense. I kind of get it now. I think the Bayesians were all over this early. And so a lot of times when you hear likelihood-based arguments, it came from Bayesians kind of early. I have a really nice argument that's going between Jack Good and Fisher. And they're talking about this stuff. Fisher was basically saying, what is this likelihood stuff? Saying that, Fisher got into it later. So some of the arguments that we heard early, we need to follow up with later arguments. But I want to just kind of say, the likelihood seems like a good idea. Now there is a principle out there called the likelihood principle, and we'll look at that briefly in chapter 6. What I'm much more interested in is conditionality and sufficiency. Now, some people will say that adds up to the likelihood principle, and some people will argue against that. I don't want to get into all of that in this class. And so I want to show you that the likelihood is an important tool for measuring what's going on in P. Okay, so this is some function. Now, to formally turn it into a measure, i.e. the probability measure on P, I need to apply Bayes' theorem. Okay, so this has the same functional form of fx given P. And that thing for us was just product. I goes from 1 to n fxi given P. So this was just product. I goes from 1 to n. P raised to the xi's, where the xi's are indicator functions. I haven't said this. So this is an element of 0 or 1. So just one of these two things. With probability P, we see a 1. With probability 1 minus P, we see a 0. Same parameterization that we always see. And so I can reduce this like this. Sum of the xi's, P to the sum of the xi's times 1 minus P times n to the minus xi's. So this is my likelihood function. And I want to be real clear about this, that P lives between 0 and 1. So that's the likelihood. And then the prior has some form as well. And last time we argued maybe a beta distribution. And I think some of the answers for why a beta models things between 0 and 1, that seems like a good idea. Are there other distributions that exist between 0 and 1? Certainly. So infinitely many. Turns out this one's a really good idea for lots of reasons, not just one. But one reason of using a beta has two parameters in there. And I'll say this thing is proportional to P to the alpha minus 1, 1 minus P, beta minus 1. So one good reason for using a beta is that I can do this multiplication quite trivially. So if I know about the beta distribution, things of this form, you want to know what the constant is here, it's 1 over a beta function. It's a beta function, it's the integral of this thing. right here. I usually call this the kernel. Oops, sorry, this thing. I usually call this the kernel of a beta. There's an integrating constant out here, and I'm usually reluctant to write it down. Now I can evaluate that. If you give me alpha and beta, I can tell you what the actual number is. I can come infinitely close to that number, I should say. So there's no closed form representation of that integrating constant. Even though we say it's a function, we know what it is, you just can't write it down. It's gamma functions, a bunch of products of gamma functions. So gamma of alpha plus beta divided by gamma alpha, gamma beta. And so where do I ever use that fact? I do not. So I really don't. So, but a beta function goes right here. But what's nice is that when I multiply this into this, these have the same forms. So things combine rather nicely. So when I do this product, I get p to the sum of the xi's plus alpha minus 1 times 1 minus p to the n minus sum of the xi's plus beta minus 1. It's the same thing that we wrote down last time. And we recognize this as the kernel of a different beta distribution. So beta is a big collection of distributions. If you tell me it's parameterization, then I have a single distribution. So to do this, I'm going to have to lock those down eventually. I'm going to have to pick what these are. But if I pick alpha and beta, the hyperparameters, we notice that this is also some beta distribution, a fixed distribution. So this thing right here is a beta. Sum of the xi's plus alpha. And then the other parameter right here is n minus sum of the xi's plus beta minus 1. So it's just an updated beta distribution. So the prior is beta, posterior is beta. So the information that we're collecting comes through the likelihood function. So some people will phrase all of Bayes as just sequential updating like this. I get a little bit more data and I'm just updating my posterior. And here's a few little tidbits that if I see more data and I form my likelihood just out of that data and I multiply by my old posterior using my old data, that's a sequential update of the posterior. So your old posterior becomes your new prior. Now, to do any calculation and show that that's true, but there's a lot of good, interesting things about Bayes, whether it's sequential updating of parameter spaces, so in time series, it's very natural to do these sort of things where you're just collecting data through time. But it's also a good decision-making tool as well. So it has good decision theoretic properties that we'll get into in chapter 7. Okay, let me just tell you that. There's a definition. If the posterior and prior both live in the same distribution, I'll say family, I'll allude to what this means in a second, then the prior is said to be conjugate. This is just a word. So the prior and the posterior are both in the same distributional family. Now I don't mean anything as big as like the exponential family. It collects a lot of distributions. It has nice limiting properties. We'll see that a little bit today. Beta is in the exponential family. Normals are also in the exponential family. They're entirely different distributions. So I mean, all I get to wiggle down in the same parametric form are the parameters underlying that distribution. That makes different distributions. So beta's in the beta family. Beta's in the beta family. So this lives in a beta family right here. This one also lives in a beta family. So we say the prior is conjugate. Why do we like that? Because if you know how to use your prior, you know how to use your posterior. And it's just this trivial updating. So it makes the math very nice. So that's not a good reason, though. It's a good reason for me to like conjugacy. So, because it makes my life easier. So, but that's not a good reason for anybody else. I need to give you other reasons. So it turns out that under certain parameterizations, I can have so-called optimal properties. So it turns out that if alpha and beta are both a half, you have transformation invariance. We'll talk about what that is briefly. I'm not going to give you a whole lecture on all this. I also have optimal coverage properties. So if I design intervals out of this distribution that I get, so this has some shape to it. So if I come up with some intervals that collect, say, like 95% of the mass in here, between two limiting points, and I define an interval by that, I can set this up so that I cover the true parameter 95% of the time, optimally, perfectly, really well, better than anybody else. That's what I mean. On average, I do better. So if you are a frequentist and you like coverage, that's the way you like to sell your intervals, then I can give you a prior that no other frequentist can beat you. So no matter how they phrase the inference. Now there's other ways to phrase these inferences that some people say it's not Bayesian, it's penalized likelihood is what I'm doing. That's okay. You can call it what you want. I'm still going to call it Bayes. So there's other ways to kind of come up with these objective sort of things, but a Bayesian would probably look at it and go, it's Bayes. So it's okay. Lots of arguments over those semantics. I want you guys to be more flexible in how we use the language. What you think something is, you can say, well, it's Bayes if I think about it like this, and if I think about it a different way, it's not Bayes. And does it matter? This is a personal question. So this prior right here can both be easy to work with and optimal in some senses. And I'll have you explore this on your upcoming homework. Any questions about all this? This is the beta binomial conjugate analysis. I really like this analysis because we start out with something that's a bunch of zeros and ones, totally discrete. We have a parameter that's constrained between 0 and 1, so it seems like a hard problem to work with. And our posterior, our inferences, should be continuous. And I want to show you something else. It also depends on this statistic right here. Some of the xi's. And we know a lot about that thing. So it has some really nice limiting properties as well. And so I will point out that this is a sufficient statistic. It's also a very special one. So I can compute this thing up here using all of the xi's, my whole vector of these 1, 0 bits. So I could form it like this, if I wanted to, or I could write it down like this. It doesn't make much difference when I write it down on the chalkboard. So still the same thing. However, these things right here, the whole collection, x1 to xn, this is n-dimensional. This thing right here is one-dimensional. There's some of the xi's. And it has the same information about p. And so this function is that function. Same thing. So this one-dimensional thing that I can just carry in my back pocket very easily has as much information as this presumably very large dimensional thing that I need a backpack to carry. Think about it on a computer. So which one do you want to compute with? One will blow out your RAM and cost you a lot of computation. So there's some theory about this, and Fisher, while he was going through things, he was trying to understand properties of statistics. And he discovered, at least in this example, quite trivially, that some of the xi's has just as much information as this. It's also, I can't compress the dimension anymore. You gotta have something. So I can't go to a zero-dimensional step. That's nothing. There's no such thing as halfway there. So this is as small as I can go. So this is minimal sufficient. We'll discuss this in chapter 6 as well. But what I'm going to try to impress upon you is the likelihood has a lot of information about what the true parameter is. And this thing does something for us. It helps penalize really what's going on in the boundaries, is how we use it. We'll see that in a moment. This can also anchor some of your beliefs. If you were a subjectivist, and I am, but a lot of times I do so-called objective things and I choose my criterions. So that also makes me subjective. I'll also try to impress upon you everything we do is a choice. So you have to choose which properties you're protecting. But if I knew something about the coin being flipped, I could parameterize this here. I could encode information. And in the last lecture, when I asked for alpha and beta, I think we said, let's let it be 3 and 2. So we picked in our analysis 3 and 2 here, and we'll look at that again. What does that mean to you? This was from last time. Alpha was equal to 3, and beta was equal to 2. Other way, right? It's 2 and 3. I can just see the picture of what we drew. It's leaning towards the left. So what does this mean to you? If a Bayesian did this and walked in with this prior, what would they be saying? It's quite intuitive. Look at the posterior and how it's treating the data next to the hyperparameter. The sufficient statistics are always sitting right next to the hyperparameter in this linear way. That gives me interpretability. I know what I'm doing with it. It has this relationship with the data in this additive form, and the data has a relationship with the data in an additive form. So it's acting like data. So somebody try to interpret that for me. Somebody says, what does it mean that you picked alpha 2 and beta 3?
So without any data collected, that's your guess of the P.
Yeah, it's kind of anchoring your guess at P. We'll look at this in terms of the geometry of the shape in a moment, but I would briefly explain this as saying, well, this is like I've seen the coin flipped 5 times, and I saw 2 successes and 3 failures. So that's how we think about it. So my prior belief is like 5 coin flips, slightly biased to the left. So that's one interpretation. Now, if somebody came to me and said, why did you do this for this problem? And I go, I don't know. That's not a great answer or a great reason. So we have to come up with answers and reasons behind our parameterizations. Let's look at this again. wrote this piece of code. This will be online for you. Play around with it. You're going to write something similar in your homework. Now, basically, this is just coin flipping. What's the matter? No? It's okay. The upcoming one, I might see what you guys, I say homework and you guys freak out. You guys are on track. So we're supposed to be turning in a homework assignment today. So that part's okay, but not this. Okay. So this will be due in a couple weeks after spring break. Sorry for the panic. So I've got this thing, and basically what it's going to do is it's going to flip coins. So all I'm going to do in all of this, got some plotting functions. I'm just going to run through a for loop iteratively. It's about the slowest way I can do it on a computer, but it's at the time of thinking. And I'm going to flip some coins for you. So I'm going to plot my prior. There it is. So I was wondering, where do I flip the coin? And I'm going to flip a coin periodically. So in my thing, I flip a coin. So what I did first is I plotted the prior for you so you can see it. So this is just me plotting the prior. How did I do it? I invoked this function called beta PDF. And I just chopped it up on a grid. So I created like 1,000 points or so. I used 100 points in a picture. I can't tell the difference. So I can't plot the whole continuum. I just plotted it points. And then what I did is I normalized it all. So I divided by the sum of all those points. And that gives me my prior distribution. I plot that for you. And then I start flipping some coins. And I update this beta PDF function using some of the XIs. And I plot that for you. So this is the parameter value observed. This is just the likelihood value. And then I multiply it by my prior. So I do this all in a bunch of different steps so that you can see. Again, this is probably the worst way to write this code. However, it's easy to walk through. So I plot my likelihood for you. Then I take my likelihood and I multiply it by my prior. That's i.e. my posterior. So I know that's another beta, and so I ended up just chopping up that beta as well and plotting that. And then I just plot them next to each other so that you can see this function evolve. Okay. 2 and 3 is what we used last time. So my parameterization is P is the true P. The only place I'm going to use this is when I simulate X's. And I'm going to also plot next to it. So I also use it in my graphs so you can see where the truth is. I'm going to do this 100 times, and P is going to be 0.7. And I'm going to do it rather fast this time. Last time, start this over. I think it's worth watching slow just one more time. So if anybody wants to know how I stop my plots or how I stall them for a second or whatnot, I use the pause statement. So here's my truth, 0.7. Here's my prior. And I've normalized that for you. And so it's kind of biased to the left. This, at least to me, is how I envision what a biased coin might look like in terms of its probability. I don't want to put all of its mass right there. I want to smear it around a little bit because I'm uncertain. So one thing that's clear, that because our posterior is prior times likelihood, we should never put a prior mass of 0 anywhere that we think that an answer might exist. Anything I multiply 0 by is still 0. And so I usually call those political priors, because no amount of data can change their mind. So they have a position, that's it. They do not move based off of data. Unfortunately, it seems like that's a lot of politics. So no matter what the data is, we're still going with what we originally believed. I flipped the coin once, and here's my likelihood function, again, P. So looks like that straight line, and here's my posterior. There was a lot of impact due to that one coin flip. Wasn't able to pull it all the way over. There's still a lot of information in my prior. I said that I've seen 5 coin flips a priori. This is like my 6th bit of information. Another head. Another head. This thing keeps growing, and I like to think about, what does this mean? It means I'm getting pretty certain that the coin has a big P parameter. And I'm not willing to discount that it's actually 1, that I'm flipping a completely biased coin, 2-sided headed coin. But I'm not willing to say that entirely. So there's still a lot of mass over here. If I look at this posterior, my probability of it being less than 0.3 is rather small. How would I quantify that? I would add up the area in this left tail to the left of 0.3. So that's what it all means. What's my probability of the coin flip having P equal to 0 as its parameterization? It's 0. This is actually 0 right in that corner. That's not possible, because I've seen 3 successes. One more, and now this whole curve inflects. I really love that flexibility. You probably didn't know a beta could do that. Flip around like that. It can do all kinds of things. And so it's certainly not symmetric in its inferences. While I'm using some of the xi's as my sufficient statistic, there's no way that that's normally distributed. Doesn't look like it. I'm talking too loud on my class. We'll keep it dead. So I'm going to keep pushing this, see what happens. Notice that the likelihood and the posterior are getting closer and closer together. So again, what that means is that the impact of the prior is wearing off. And I like that. So if you're an asymptotic sort of person, there's no good reason to not be a Bayesian. Lots of good asymptotic properties. And that curve is starting to look more and more normally distributed. And you can kind of eyeball that. So I can overlay a normal and notice that they're getting closer and closer and closer to each other. And that's simply because my sufficient statistics, some of the xi's, tends to be normally distributed and gets bigger and bigger. Now I didn't need to know any of this to do the analysis. All I need to know is, you give me a good prior, I can write down my likelihood because you gave me the sampling model, and all these great things happen for free. So let's just run it a couple more times. I want to point out that if I ended up, let's not pause at every step. If I ended up biasing my prior a lot, so let's do that. Let's imagine alpha was 200 and beta was 300. It's the same beliefs, right? I see the same proportion of tails to heads. So 200 heads out of 500. So 2/5. But it's not the same, because I'm changing the variance of that distribution quite a lot. So I really put a lot of emphasis on that belief by counting those zeros. Let's see what happens. My prior is here. Doesn't even fit on the screen exactly because it's so sharply pointed. So what I'll try to teach you is that if you do a Bayesian analysis, make sure your prior is not too pointed. You're putting too much mass somewhere. My likelihood function's over here. My likelihood seems to have a lot of information in it about where that true parameter is. My prior is stacked way over here, and the posterior is somewhere in the middle, but I bias the analysis quite a lot with my prior. And so we probably don't want to do that. What we would like is a prior such that it's got good properties and my posterior can drift away from the prior as fast as possible. Now to come up with that, you need to come up with the notion of distance between distributions. If I invoke Kullback-Leibler, and I do that, so that's not a distance function, it's a divergence function, but it has a measurement of the discrepancy between two distributions. So it's the log ratio of the densities as I integrate across them with respect to one of the measures. So the log of a ratio, if they're the same, is 0. So we'll talk about that later in class. This is a much steeper mathematical concept. And then I say I want the limit to make these things diverge as fast as possible. Turns out there's one prior distribution that will do that for you. And it's beta half-half. So it's another beta. So another reason to like these betas. I'm just going to try to compel you that this is all very reasonable, but a beta 200, 300 is probably not a good choice. So let's pick a uniform distribution. That's a beta 1, 1. So alpha, or p to the 1 minus 1 is 1. And 1 minus p to the 1 minus 1 is also.
So is this like no data points to start with?
No. It does have some amount of information, right? It's like I flipped 2 coins, and it was fair.
So if that's the case, then the match would be 0 and 0 and 1, right?
This is just a uniform prior across that does have information in it.
Right.
It's not like 0 coins were flipped. There's still a penalty there. Think about the posterior, sum of the xi's plus alpha, and minus sum of the xi's plus beta. I'm adding 1 to each one of those. So it's like I've seen 2 coin flips. I'll let you think about it. There's my posterior wiggling around. I got a sequence of zeros to start with. So I got unlucky in the coin flipping. This is a simulation. If my simulations always turn out to be pristine on the first time I run them, there's something wrong. Periodically, we should be off. That's what a statistician is trying to tell you all the time. You cannot have perfect predictions. So this is what we got. How's that look? I'll tell you where some of the xi is probably. It's probably somewhere around there. So with this set of data, everybody would have done fairly poorly. So this is where I try to convince you that n is equal to 30 is not good enough a lot of times. Let's run it one more time. So I want to remind you what we saw last time is that we had our bell, 0.7 was over in the tail. So if you think about this, just think about using the normal theory, some of the xi's. How often should our 95% interval cover the truth? 95% of the time. Every once in a while, the true parameter is out of the tail. That's our error rates. How's that for an answer? Better. And so, where's some of the xi's? It's like in the middle right here. And so the Bayesian is going to quantify where they think the truth is using this shape. So the Bayesian answer is the posterior distribution. What you do with it, how you make decisions, we'll get more into in chapter 7. Okay, here's my favorite prior, the half-half one. This is what most people would use. This has optimal coverage properties. It's also unbiased. So it's like flipping a half coin. So it's like I flipped one coin on each side. And basically what I'm doing is I'm ruling out that the parameter is 0 or 1 by doing that. So I don't want to place too much emphasis on that. And this prior looks like this U-shaped thing. So what it's doing is it's putting a little bit of mass right here and right here. So I want you to think about this just a little bit. If I had a coin, let's say the true parameter was like 0.0001, something small, and I flip the coin 100 times. It's very likely that I get a vector of 100 zeros. So true parameter is 0.0001, small. And so the true parameter is not 0. If I ended up looking at my maximum likelihood estimator, i.e. x bar, we'll get into that in chapter 7, we would estimate everything with 0. If I constructed my normal interval using my variance function being 1 minus x bar, 1 minus p hat times p hat divided by n, would also have 0 variance. It'd be a horrible asymptotic answer. So it's kind of like going out into the sea and trying to count how many fish there are by using a cup. So I go out into the sea, I know there's maybe some fish out there, I scoop up a cup of water, and I try to count how many fish are in there. And I estimate the whole sea using my count, and I say there's 0. It's a bad answer. And so what this prior is doing is it's guarding against that. Putting a penalty on the boundaries. It's a good idea. Turns out, the coverage rates that I can construct from 95% intervals can be optimal. So I can construct my shortest intervals that cover at the optimal rate. And that's kind of cool. Beta half does that. Very little penalty, so the effect of the prior wears off very quickly. It's also unbiased. So my prior is centered at 0.5. So it's not going to give any weight to each one of them without giving the same amount of weight to the other one, but it's also making it very little weight. Now you might say, hey, why don't I just take alpha and beta and turn them into 0.0001? Something like that. It'll still stack up all the mass right here at 0.5, and it'll shove these things closer to the walls. Saying that, the data will take a little bit more time to overcome that. If you did happen to do that, it wouldn't be that big of a mistake. So you'd barely notice it unless you're working with like 4 or 5 data points. So I hope this illustration kind of tells us that Bayes has something that's kind of cool. So that's about how a Bayesian thinks. Should we do one more analysis before I give you your homework? I'll give you your homework next time. How's that? What I'm going to ask you to do is I'm going to ask you to make inferences about this parameter. You can call this whatever you want. So instead of doing inferences about p, I want you to do something about a function of p. And I want you to make inferences about it. How does a Bayesian do this? Just to see if you all were paying attention. How would I do inference on that parameter?
First, you set a prior distribution that you p over 1 times p is coming from.
Okay. Okay. So I need to start over, right? Any other answers? Maybe. This is where this class gets confusing. Don't do the delta method on it. So the delta method might be a substitute method for this, so you could, but it's a really funny answer to do that. Then
You could transform the posterior we already have.
that's it. So that's all you have to do. So we have this posterior. And so if I wanted prior beliefs that have the same implications on P, then I would just use those prior beliefs from P and transform everything. So I would transform this distribution to this distribution. So I'll say G of P, which is just P over 1 minus P. So there's an implied distribution that just falls right out of that. If I knew how to sample from this distribution, i.e. a beta distribution, right here, then I could take all my samples and just plug them into this formula. Or I could do the math and figure out what is this distribution. Does anybody know what this distribution is called? This is going to be a beta plot. So what I'm going to have you do is I'm going to have you sample from a Bernoulli distribution n times with some parameter. I'm going to have you apply the delta method, bootstrap, and Bayes to infer what this parameter is. And I'm going to have you change n and p and do it again. And do it again, and do it again, and do it again. So you're just going to run this over and over again in a for loop, and you're going to see how well these methods compare to each other in a frequency setting. And I bet a lot of your opinions change about a lot of things as you do that. So the math is cool, seeing the picture is cool, but also comparisons kind of conclude the story. And some of you might come up with different conclusions to that story. I'm going to give you a homework that outlines the full simulation study. I'll give it to you. I'll put it up tomorrow, and then I'll walk you through it on Wednesday. I would encourage you to read through it before coming to class. Let's do one more example. Make sure we got this. Let's start real easy. And a lot of people start with this example because it is easy. But I like starting with the Bernoulli distribution because you have to think about a lot of things with it. Example, xi's come from a normal with mean mu and variance sigma squared. And I'm going to say you know this. I goes from 1 to n. IID samples. What we want to do is infer this. So a Bayesian wants to construct the posterior distribution. And I'll be a little bit overkill in my parameterization right here, just to let you know that you always know sigma squared in here. So a lot of times I like to write that down. And so this is our goal. So this is the posterior distribution for mu. So there's only 2 ingredients in a Bayesian analysis. What are those? So, likelihood. I'm going to write it down for you real quick. I'm going to invoke a few things that I know. And if you don't know this, you're going to learn it in the coming weeks. But the likelihood looks like this. I goes from 1 to n, 1 over root 2 pi. I could get rid of that if I wanted. Divided by sigma, I could get rid of that if I wanted to. They're constants. E to the minus 1/2 xi minus mu squared over sigma squared. And I can work with this product if I wanted to, but it's a bit messy. Turns out this is proportional to this. E to the minus 1/2 x bar minus mu over sigma squared divided by n. And it's just math showing that. Just expand everything out, be complete square. So, or you could have already known x bar is the sufficient statistic for mu. So, hopefully I can convince you. You usually use x bar to estimate mu. So it turns out x bar is sufficient, and the distribution of x bar looks like this. Lots of different ways to capital S. What prior do we want? So this is proportional to e to the minus 1/2 x bar minus mu. Sigma squared over n times pi mu. What prior would you like? Let me come up with a very easy one. Prior is just flat. And I know this is fast. And if you've seen this before, you'll go, wow, that was really quick that you just did that. So what are you talking about? So this would have bothered me a lot if somebody did this, but let me show you something really cool about this. This is why I can do this calculation super fast. Pi mu given x is going to be equal to e to the minus 1/2 x bar minus mu. I'm going to spin this around. Mu minus x bar squared over sigma squared over n. I'll say this is proportional to that right here. How did I do this? I took that function and then multiplied it by 1. And I noticed that if I spun these two things around, still the same value because I'm squaring everything. This right here is a normal distribution centered at x bar, and it has variance sigma squared over n. Does that look familiar? Let me ask you what a frequentist would do. And again, it's all chapter 7 stuff. We're just way ahead of the game now. Spent a lot of time going over preliminaries, but now we just surged ahead. So what does a frequentist do? Frequentist knows that the sufficient statistic is x bar. So they build the distribution on x bar, and they use that to say something about mu. So they usually use this distribution right here to characterize what they believe mu is. They'll build their intervals out of that distribution. And frequentist will build maybe a 95% interval by looking at x bar plus or minus. So let's say x bar plus 1.96 sigma over root n. And they'll let this one be x bar minus 1.96 sigma over root n. And they'll say something like, that interval will cover the true parameter 95% of the time. And if you were in Stat 101, you might say, does that mean that I believe mu is in that interval? What happened to you when you said that? So if you did build that interval and you said, that's where I think mu is. And usually everybody came rushing back and said, you cannot think that. It's not what you believe. That covers the true parameter 95% of the time. Well, if you're a Bayesian and you're working with a flat prior, you would construct a distribution on mu. So this would actually be my mu's distribution. This is given sigma squared. And I would have a probability distribution on mu, and the 95% shortest interval would be those exact same points. And a Bayesian is using this distribution to characterize where they believe mu is. It's the posterior distribution of beliefs on mu. So if you could go back a few years to your Stat 101 teacher and say, actually I'm a Bayesian, I use flat prior. I like my answer that I believe mu is there. Here's what I just told you. You can have it all by being a Bayesian here. This does have optimal coverage, just like the frequentist does, the typical frequentist. Optimal coverage, and it's belief. Turns out it's also the minimal impacting prior. You follow that 5-second dialogue, what I told you what a reference prior was. It has that property as well. It's also transformation invariant. So in any transform space, it has optimal priors. So it turns out with this analysis, you can have everything. Let me ask you just one more question. Was this prior that we just picked conjugate? You know the answer, David. You think so? You think it is?
Well, that's an improper prior, so.
Okay, so David knows the game here. It's a limit of conjugate priors. So it's not conjugate itself, this is flat. And our posterior distribution is anything but flat. But what David knows is this is a limiting sequence of normal conjugate priors, where the variance is being made go bigger and bigger. Let's come back, say a little bit more about that, 15 minutes, and then I want to jump into chapter 6 and get into sufficiency. So I think that's where we're at now. So think about all the questions that may have just sprung to your mind, because this was a lot of information. And in chapter 7, when we come back around to estimation, we're going to see a lot of this. But I bet you have lots of questions about what we just did, what the implications are. But what I did say is if you were a Bayesian in this analysis, you get every optimal property for free, even the frequency. That's awesome.